So, dear colleagues, I'm glad to meet you at our day session. And the first talk of our session is Professor Naoya Ando from Kumamoto University of Japan. And his talk is Surfaces with Flat Normal Connections in Four-Dimensional Space Forms. Please, Professor Ando.
Thank you very much. I'd like to express my cordial gratitude to the organizers for giving me the chance of this talk. I will talk about surfaces with flat normal connection in four-dimensional space forms. Uh, the main contents of this talk are found in these two preprints. The first preprint is the first preprint has been completed last week. And the second preprint was completed by Hatanaka and me. Hatanaka was a graduate student of my laboratory, and now he is employed in Japanese company. In section 1, I will explain the connection of the twofold exterior power of the pullback bundle on a surface. In section 2, I will explain the equations of Gauss-Kodach and Rich. In particular, we see that these equations are closely related to twistorial discussions. In section 3, I will explain surfaces with degenerate twistor lifts. The degeneracy of the twistor lifts on a surface is equivalent to that the surface satisfies the two conditions. Condition 1, the curvature of the surface with respect to the induced metric is identically equal to the constant sectional curvature of the space. Condition 2, the normal connection is flat. In section 4, I will explain space-like or time-like surfaces in neutral or Lorentzian four-dimensional space forms. Let NH be a four-dimensional Riemannian space form. Then H is its Riemannian metric. If N is flat, then NH is the Euclidean four space. In the other cases, N is either the four sphere or for hyperbolic space. Let M be a Riemann surface, and let F be a conformal immersion, and let UV be local isothermal coordinates. Then the induced metric G of M by F is represented like this. Lambda is a real valued function. Let T1, T2 be like this, and N1, N2 be normal vector fields of F, satisfying these conditions. In particular, N1 and N2 are orthogonal to each other. Suppose that the space N is oriented and that this ordered local frame field gives the orientation of the space. Let E1, E2, E3, E4 be given like this. And let theta plus minus 1, theta plus minus 2, theta plus minus 3 be given like this by E1, E2, E3, E4. The twofold exterior power of the pullback bundle on M is decomposed into two sub-bundles of rank 3. This bundle is of rank 6, and these sub-bundles are of rank 3. These local sections form local orthonormal frame fields of these sub-bundles, respectively. Let nabla be the Levi-Civita connection of the space. And nabla hat the connection of the twofold exterior power induced by nabla. Then nabla hat gives connections of these two subbundles, and we obtain these relations. T1, T2 are like this. Here, double plus minus, x plus minus, y plus minus, z plus minus, phi plus minus, psi plus minus are functions. These functions are given by these relations. Alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3 are given by these relations for the second fundamental form sigma of F. And phi plus minus, psi plus minus are functions given by these relations. And mu1, mu2 are functions given by these relations for the normal connection of F. Let R hat be the curvature tensor of nabla hat. And let we denote by L0 the constant sectional curvature of N. Then we obtain this relation. We can express the left-hand side by w plus minus, x plus minus, y plus minus, z plus minus, and so on. And using these relations, we obtain these relations. The first two relations are equivalent to the equations of Gauss and Ricci, and the other four equations are equivalent to the equations of Kodach. Originally, the equations of Gauss, Kodach, and Ricci are obtained by the Gauss-Weingarten equations. These equations can be rewritten into these relations directly. But in this situation, computing the left-hand side, we can also obtain these relations. Let large K be the curvature of the induced metric G of the surface. Then K is represented like this by the function lambda. We say that the normal connection of F is flat if the curvature tensor R pub vanishes. This condition is equivalent to this relation between mu1 and mu2. Mu1, mu2 are given like this relation. The twistor rifts of F are sections of the twistor spaces associated with the pullback bundle and locally given by theta plus minus 1. Theta plus minus 1 are given like this. The twistor rifts of F are said to be non-degenerate if for each epsilon plus or minus. These covariant derivatives of theta epsilon 1 by T1 and T2 are linearly independent at each point of M. The twistor rifts are said to be degenerate if for each epsilon, these covariant derivatives are linearly dependent. Then, noticing the first column of the matrix, we observe that the following three conditions are mutually equivalent. Condition A, the immersion satisfies these two conditions. Condition B, the twistor lifts of F are degenerate. Condition C, delta plus minus, defined by these, vanish. These three conditions are mutually equivalent. The twistor lifts of F are non-degenerate if and only if delta plus minus are non-zero because of these equivalence. If we suppose that delta plus minus are non-zero, then the equations of Kodach, these are expressed by these relations. Noticing these relations, the equations of Kodach are rewritten into these relations. Phi plus minus are equal to A plus minus. Psi minus plus are equal to B minus. Here, A plus minus, B minus plus are represented like this. Noticing, noticing that delta plus minus are represented like this by double x, y, z. We see that A plus minus, B minus plus are represented by double x, y, z. Using A plus minus, B minus plus, we can obtain characterizations of surfaces such that the twistor lifts are non-degenerate. In this section, I will explain surfaces with degenerate twistor lifts. So, such surfaces satisfy these two conditions. If F has a parallel normal vector field, then the second fundamental form sigma satisfies the linearly dependent condition. That is, F satisfies this relation for a function theta. If sigma satisfies the linearly dependent condition, then the normal connection is flat. Suppose that the curvature of the surface is not equal to L0. This is the constant sectional curvature of the space. Then F has a parallel normal vector field if and only if sigma, the second fundamental form sigma satisfies the linearly dependent condition. If we suppose that k is identically equal to L0, then the linearly dependent condition of the second fundamental form does not necessarily mean the existence of parallel normal vector fields. Suppose that there exist nowhere zero functions small k plus minus satisfying these relations. Then noticing noticing the definitions of delta plus minus, we see that if we suppose these relations, then delta plus minus vanish. So F satisfies these two relations. By these relations and the equations of Kodach, these are the equations of Kodach. Then we by these relations and by long calculations, we see that there exist functions small f plus minus satisfying these relations. So large x plus minus and y plus minus are expressed by small f plus minus and small k plus minus. by the equation of Rich, we obtain this relation between small f plus and small f minus. we denote this function by large B. Therefore, if B is not equal to 0, B is not equal to 0, then there exists a function psi satisfying this relation. Suppose that large x plus minus and y plus minus satisfy this condition. This is not equal to 0. Then we can show that sigma does not satisfy the linearly dependent condition. So in this situation, the surface has no parallel normal vector fields. By the definitions of double xyz, and by the definition of these functions, we see that the sum of double plus and double minus is equal to the sum of x plus and x minus. Similarly, the sum of y plus and y minus is equal to the sum of z plus and z minus. So we obtain these relations. Applying these relations to these relations, we see that small k plus and small k minus are expressed by x plus minus and y plus minus. Notice that this denominator is non-zero because of this condition. Applying these relations to the, sorry. ちょっと、sorry. Applying these relations to these relations, we obtain the only one relation, this relation. K plus is expressed by K minus large A and large, large A and large C. Here, large A is given by this. This is not zero because of this condition. And C is given by this. By direct computations, we obtain these relations. Applying these relations and this to the equations of Kodachi and by long calculations, we obtain this relation. This is an overdetermined system with respect to the function gamma. Gamma is a function satisfying these relations. Such a function as gamma exists because of we suppose this relation. So there exists such a function as gamma. Theta minus is a function given by this. Theta minus appears in this term. A prime is given by this. This is not there. Sorry. This overdetermined system gives a characterization of surfaces with degenerate twistor rifts and satisfying the condition that the second fundamental form does not satisfy the linearly dependent condition. This system gives a generic characterization. In addition, if L0 is equal to 0, then we obtain this relation because if L0 is equal to 0, then the surface is flat. So the function lambda, this function is used in the definition of the induced metric of the surface. Then we can suppose that lambda is constant, non-zero constant. Yeah, no. Lambda is constant, we can suppose. So, if L0 L0 is equal to 0, then we can we see that this term vanishes. So we obtain this condition. Noticing that gamma u, gamma v, theta minus u, theta minus v, f minus u, f minus v. Noticing these functions, we see that there exists a function xi tilde of one variable satisfying this relation. This is expressed by a function xi tilde of f minus. Because of this. By this relation and this relation, we obtain by long calculations, we obtain this relation. This is an overdetermined system with respect to the function psi, and A, B, C are R2 valued functions constructed by F minus and Xi tilde F minus. The definitions of A, B, C are not short. So I don't write the strict definition the strict definitions of ABC. I don't write. This system gives a generic characterization of surfaces with degenerate twistor lifts and the condition that the second fundamental form does not satisfy the linearly dependent condition. In the above discussions, we suppose that the space is Riemannian, our Riemannian four-dimensional space form. In the case where n is neutral, analogous discussions and results are valid for space-like or time-like surfaces. In the case where n is Lorentzian, analogous discussions and results are also valid for space-like or time-like surfaces. However, in this case, we need the decomposition of the complexification of the twofold exterior power of the pullback bundle on a space-like or time-like surface. Let NH be a four-dimensional Lorentzian space form. Then small h is the Lorentzian metric of the space. Let M be a Riemann surface. Let F be a space-like and conformal image. Let UV be local isothermal coordinates of M. Then the induced metric G is represented like this, as in section 2. as in section 1 から。Sorry. And let T1, T2 be like this. And let N1, N2 be normal vector fields of F, satisfying these relations. Notice this minus. Notice this minus because the space is Lorentzian. Suppose that n is oriented and that this ordered local frame field gives the orientation of the space. Let E1, E2, E3, E4 be given like this. And let theta 1, theta 2, theta 2 be given like this. And notice that uh, the imaginary unit appear. This is the imaginary unit, the square root of -1. The complexification of the twofold exterior power of the pullback bundle on M on the surface is decomposed into two sub-bundles of complex rank 3 and theta 1, theta 2, theta 3 form a local frame field of this sub-bundle. And theta 1 bar, theta 2 bar, theta 3 bar, the conjugates of these local field form a local frame field of the other subbundle. Let nabla be the Levi-Civita connection of the space. Then nabla induces a connection nabla hat of the complexification of the twofold exterior power of the pullback band naturally. In addition, nabla hat gives the connections of these subbundles. Then we obtain these relations uh, based on the Gauss-Weingarten formulas. Here, functions double x, y, z, phi, c. These are given by these relations. Notice that this is the imaginary unit, the square root of -1. By these relations, we obtain these relations. The first relation gives the two equations from the real part and the imaginary part. These two equations are equivalent to the equations of Gauss-Ricci. The other relations gives four equations, and these equations are equivalent to the equations of Kodachi. Referring to section 2.3, we can obtain analogous results for space-like surfaces in N. For a local complex coordinate double defined by this U, V. The real part of double is U. The imaginary part is given by V. Then we have by these relations, we have this relation. Double bar is the conjugate of double. So whether this covariant derivative of theta minus by the double bar vanishes or not is determined by F and does not depend on the choice of a local complex coordinate. And this condition is we easily see from this relation that this condition is equivalent to this relation. In particular, if this covariant derivative vanishes, then this holds. So, noticing the first column of these matrices, we see that the covariant derivative of theta minus by T1 and T2 are linearly dependent. So we see that the complex twister lifts are given by theta 1 and theta 1 bar, and this condition gives a special class of space-like surfaces such that the complex twister lifts, which are given by theta 1 and theta 1 bar, are degenerate. The degeneracy is defined similarly as in section section 2. And we can obtain a characterization of surfaces with this condition. Let M be a Lorentz surface and F a time-like and conformal immersion. Let UV be local coordinates of M, compatible with the paracomplex structure of the Lorentz surface. Then the induced metric G of M is represented like this. Lambda is a real valued function. Notice this minus because the surface is time-like. So the signature of the induced metric has plus minus. Let T1, T2 be like this, and N1, N2 normal vector fields of F satisfying these conditions. Suppose that N is oriented and that this ordered local frame field gives the orientation of the space. Let E1, E2, E3, E4 be given by these. Notice that this is N1, this is N2, this is T1, this is T2. In the space-like case, T1, T2, N1, N2. But in the time-like case, we set N1, N2, T1, T2. Then the conjugate of theta 1, theta 2, conjugate of theta 1, theta 2, theta 3, theta 1, theta 2, theta 3 are given like this. The conjugates of these theta 1, theta 2, theta 3 are represented like this. And these local fields, these local fields form a local frame field of this subbundle. Then, by the Gauss-Weingarten formulas, we obtain these relations. Double XYZ and phi psi are given by these. Notice that these double XYZ phi psi are completely identical to the sorry. These functions are not completely identical to these functions. For example, this double is given by alpha 2 minus the square root of minus 1 beta 1. But in the time-like case, this double is given by alpha 2 plus the square root of minus 1 beta 1. And this z is given by beta 2 minus the square root of minus 1 alpha 3. But in the space-like case, this is plus. So these functions do not coincide with the space-like these functions in the space-like case. By these relations, we obtain these relations. The first one is equivalent to the equations of Gauss and Ricci. And the other equations are equivalent to the equations of Kodach. Referring to section 2.3, we can obtain analogous results for time-like surfaces in the space. My talk has finished. Thank you very much.